Okay, so off we go to our second video in the Demobras Theorem series. I'm going to start with a little bit of review. So if you really feel like you have the first part down, feel free to skip over the first part of the video. I'm going to get into the more advanced pieces as I get near the end. But I wanted to start kind of from the beginning in case people are struggling with some of these concepts. So let's just remember a couple little things. So in Demobras theorem, we have two different systems. We have A plus BI, which is kind of based on that rectangular system where you move over and back in what appears to be the XY plane. Like this one goes to the left 6 and down 6i. That kind of situation. This particular side right here, obviously I'm playing with some unit circle. You should be able to look at that and realize that's a 45, 45, 90. So my modulus or radius, if you call it that, is going to be 6 roots of 2. And of course, the angle is some kind of a pi over 4, but it has to be a pi over 4 in the third quadrant. So we could probably best call it 5 pi over 4, although some of you might choose to call it negative 3 pi over 4, because we could have rotated down. Because remember, in these polar ideas, there's an infinite number of answers. Now, you also want to remember what cis stands for. That stands for cosine theta plus I sine theta. Similarly, in this problem, I was also playing with the unit circle. It should look like a neon sign every time you see that number with the number root 3. That always, now you can do the Pythagorean theorem and come up with the number 8, but it's fairly clear. And again, I just personally like to look at the easiest ratio, and I noticed that the sign opposite over hypotenuse would be 4/8. I'm ignoring the I. 4/8 is a half, and I know that the sine is a half at pi over 6. So this angle right here must be a version of pi over 6, and that version I would pick is negative. Now, sometimes when we're dealing with these problems, we're grabbing the calculator real quick, we get a number that is not a unit circle problem, like this one right here. That went to the left 7, it went down 2i, 49 and 4 makes 53. So the modulus is root 53. And of course, the angle becomes a little bit harder for people. So we could use some inverse trig games if we wanted to, or what we could do is we could hit the angle button on my calculator. It really doesn't matter if you're in degrees or radians. You know me, I prefer radians. It's fine, but I'm going to go to the angle, and I'm going to tell it to give me the angle. And I don't hit -7 minus 2i. I just do -7, comma, -2. And my calculator is going to say it's -2.86 radians. That's coming down this way, -2.86 radians. And that's a good answer. Now, of course, if we wanted to put it into degrees, that would be completely valid. And that's -164 degrees, which I think for a lot of people, that makes more sense because you can visualize that that's almost 180 degrees going backwards, so that makes sense. Now, going the other direction, if we want to take it from this cis version, which is r cosine theta plus I sine theta, we can go ahead and go the other direction. So the cosine plus I sine, and this is just nice, easy unit circle. The cosine of 3 pi over 4 is negative root 2 over 2. The sine of 3 pi over 4 is positive root 2 over 2. And we end up with a -6 roots of 2 and a positive 6i roots of 2, and we're done. Similarly, this is another unit circle problem, and I purposely did make it a little bit harder because I know that any kind of pi over 6 on a cosine is root 3 over 2. I know any kind of pi over 6 on a sine is 1/2. I just have to decide on pluses and minuses. So I kind of go over here and let's see, that'd be 6, 12, not quite 18. So since it's in the second quadrant, I know that the cosine is negative and the sine is positive, which leaves me with -9 roots of 3 and a plus 9i. And you'll notice that has a very similar feel to this one, and notice the pi/6 reference angles in both. Now, of course, last, sometimes you just get a problem. It's not unit circle. We have no choice. Notice it is in degrees, so I'm just going to just run with it. I'm just going to say, hey, calculator, what is negative 28 times the cosine of 147? And the calculator says that's 23.483. And then I'm going to ask the same question, but I'm just going to switch it over to a sign, and that's minus 15.2499 pi. And it's literally that easy. But there is a little check that we have because 147 degrees is in that quadrant. And I think quite clearly in the second quadrant, the sine portion, actually something seems, oh, that's right. It was going 147, but it has a negative radius. So it went back this way. So that makes sense that it went to the right and down. All right. Now, that was the intro. Now here comes the actual Demobras Theorem part. Now I proved in class why these formulas work, but for right now, we're not going to worry about that. We're just going to look at using them. The deal says if you multiply two complex numbers in this form, all you do is multiply their radii and add their angles. So right here, the radii or modulus is 12 and 6, so I have 72. I go ahead and add these two together and I'd get, what, 365 degrees. And literally that is a valid answer in that form. And this time I'm just going to leave it in that trig form. Over here, if we're dividing, I just divide the modulus. That's 12 divided by 6. And then I subtract the radius. 145 minus 220. I don't know why I'm using my calculator on that, but I'm not trusting myself. It's kind of early in the morning right now. So I'm feeling a little tired. So there we go. That's our story. Now, sometimes we get a little bit harder. So notice these are unit circle values. So this time I am going to take it a tiny bit further again. We're going to go ahead and multiply the modulo. That's 36. And then I'm going to add the angle. So this is 9/6 plus 1/6. This 10/6. But I'm going to reduce that down to 5 pi over 3. Now, like we did in the earlier one, I just have to think of what is the cosine of 5 pi over 3. And the cosine of 5 pi over 3 is positive 1/2. And the sine of 5 pi over 3 is negative root 3 over 2. So that would be 18 minus 18 roots of 3 pi. Beautiful. So normally when we do these problems, we do like to answer them in a plus bi form. And then over here, if we're going to divide them, 18 divided by 2, of course, is 9. And if I took 9 pi over 6 and I subtract pi over 6, I get 7 pi over 6. And the cosine of 7 pi over 6, remember 7 pi over 6 is here. So both things are going to be negative. The cosine is root 3 over 2. The sine is 1/2. And my final answer is right here, because we just distribute. And you'll notice the 9/2, root 3. It has that 30, 60, 90 kind of feel. Now, really where we're trying to go with this is these problems down here. And that was a pretty lengthy lead into that. But the first thing that I like to do is I try to think of z as 1 plus I, which of course is over 1 up 1. Which has a modulus of root 2, and it's an angle of pi over 4. So Demobras theorem says if I'm going to take z and I'm going to raise it to the 6th power, I take root 2 and I raise it to the 6th, and then I take the angle and I multiply it by 6. So that would be 6 pi over 4, or 3 pi over 2. Now, root 2 to the 6 is actually a pretty nice number. It's 8. And then I come into here and I say, well, what is the cosine of 3 pi over 2? Now, again, 3 pi over 2 is straight down here, pointing at the value 0, -1. So the cosine is 0, and the sine is -1. So the cool thing is this answer, all of that stuff in the middle just canceled out. Now, there are things that you can do to check your answer. You could hit 1 plus I on your calculator. Now, I is actually just above the decimal point on the calculator. If you hit second decimal point, that's your I. And if you raise it to the 6th, my calculator does a nice job to check that answer. Again, I am only using that to check my answer. And I could do similar things to the problem above. But for right now, I'm just going to not try to make the video too long. Now again, over 2, up 2 roots of 3i. That's again playing with that 30, 60, 90 thing. That's going to be a 4 again. So my z is 4. I notice that the angle is pretty nice. 2/4 or 1/2 is really nice. So that makes it a pi over 3, because remember the cosine of pi over 3 is a half. And then I'm going to take this thing to the 5th power. Well, then 4 to the 5th power, and then multiply the angle by 5. There we go. Now, the 4 to the 5th is not a nice number. It's pretty big. It's 1,024. And the cosine of 5 pi over 3 just so happens to be a number we've seen already in this video. 5 pi over 3 is down here, where the cosine is positive and the sine is negative. Now, again, these are unit circle. The cosine of any kind of pi over 3, the sine of any kind of pi over 3. And so, long story short, this is 512. This is 512 roots of 3i. And I, that's probably not a number that you would recognize when we do it right here, but I'll kind of show you how that works. If we took 2 plus 2i root 3, I choose to put the I first, just so it's clearly not in that radical, but you could put it afterwards. And I raise it to the 5th, I'm going to get this crazy looking decimal. 512, which you see right here, minus 886.81, blah, 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 I, well, let's see, what's negative 512 root 3, you're going to notice is, in fact, that number, again, but it still has that I. So I could validate that. Now, this one is not so pretty. This, again, not unit circle. So 1 minus 2i, that's going to have a modulus of root 5. And just as I modeled before, I'm going to go ahead and I'm going to use my calculator to find that angle, whatever that angle is. So go to angle 6, type in 1 comma negative 2, and I'm going to store that as a, because I want to know what that angle is. I got negative 1.107. So z to the 4th is going to be root 5 to the 4th, CIS, again, 4 of those. And I guess, I think I'm going to store this one instead. Let's go ahead and restore that one, because that's actually the angle I'm going to use. So what I've got now is, by the way, root 5 to the 4th power is actually 25. So here we go. And again, I stored this thing. So the cool thing is if I took 25 cosine of A, that's the cis part, that got me negative 7. And that seems strange that all of this crazy, weird decimal stuff turned into a whole number value, but there's a good reason for that. And then if I do 25 sine A, I get 24i. And the reason it kind of makes sense that that's all nice numbers is if you took 1 minus 2i times 1 minus 2i, you'll notice that there's not a decimal or a fraction to be found in that product. All of these things are going to be nice whole number values. So the crazy thing is you get this horrible looking irrational number, but the mathematics just works and brings it around all the way to square one. This problem using the method that you did back in Algebra 2, which is like full distribution, 1 minus 2i plus 4i squared. This, of course, is going to be the same. 4i squared is negative 4. So that's be negative 4 minus 4i. Oh, that's also this. And then if we distribute one more time, this is what's going to happen, because the first is going to be 9. I've got a negative 12 and another a positive 12i and another positive 12i makes 24i. Negative 4i and negative 4i is plus 16i squared, which is negative 16. And you do get the same answer. In some ways, this is far easier mathematics, but there's a lot of steps. And the bigger the exponent, the more steps. Whereas in Demobras theorem, the exponent being a 4 or a 5 or a 10 really doesn't make it any more complicated. And since we have some technology to assist us in our process, it just works better to leave it alone. So that's anyway the end of the journey that I have for Demobras Theorem Part 2. In the next video, we're going to go ahead and change some of those exponents. Instead of raising it to the second or third power, we're going to raise it to some fractional powers and investigate some roots. So that's it. See you back in class. Bye-bye.